Why do we use de-icer to keep our roads from icing up or antifreeze to keep our engines healthy in our car? The reason is because of colligative properties. And so today we're going to find out why we use salt or de-icer to melt ice and what actually happens with that. So grab a place to take your notes and let's get started. So the first thing is what are these colligative properties? And we actually know that colligative properties are physical properties of solutions that are affected by the number of particles in solution, not the identity of the solute dissolved. And so what that means is that it's about the total number of pieces or particles that we have that actually impact these properties. And there's really four main ones that we're going to look at today, and they are osmotic pressure, and so we can kind of think back to our biology days on osmosis, vapor pressure, boiling point, and freezing point. And so freezing point is where we get into our de-icer. So let's take a look at what happens with each one of these, and then we'll look at the final calculation with boiling point and freezing point. So with osmotic pressure, we see that it is increased as we add more solute to our solution. And so water moves from an area of low solute concentration to an area of high solute concentration. And when that occurs, we see that it actually is going to have a pressure differential happen, okay, or there will be a difference in pressure. And so what you can see on this diagram is if we start off with two different solutions, and on this side we're just going to have regular water. I'll get a different color here. So we have, say we have distilled water over here, okay? And we have a membrane that separates these two right in this location. And the only thing that can move past is the water. So the glucose molecules are going to not be able to move past. But we have a higher concentration. So the symbol for concentration are these brackets for our glucose on one side versus the other. And what happens is the water, we're going to have a net movement of water in this direction. So this is going to be our net movement of water from an area of low solute concentration until it gets to an area of high solute concentration. And what we see is that the difference in the level, okay, so here's where we end up with, so once we hit equilibrium here, dynamic equilibrium, there, the water molecules may still be moving back and forth, but this is going to be the overall effect. And so this difference between them is that osmotic pressure, and we can actually add outside pressure to equalize those back out. And so this is what osmotic pressure is. So the greater the concentration of the solute on this side, the greater that osmotic pressure will be. And so that is one thing that we see. And you can think about the cells and how water will move in and out of the cells and how pressure may change as a result of that in isotonic and hypertonic solutions. And hypotonic solutions, okay? So that's just one thing to kind of consider, and you can go back and maybe do some research on cells and how that works. So another one is vapor pressure, and vapor pressure will actually lower. And so the reason why is when we talked about the solvation process, we said that we had all of these little particles. So if we had sodium chloride, so we had sodium particles that were surrounded by the opposite charged end of our water molecules, which were the oxygens, which are slightly negative. And they form these shells that form around this particular particle. And it's going to do that for the sodium, and it's going to do that for the chlorine, or the chloride, I should say. And so we see that they surround them. Well, now that they're in these what they call shells, they're kind of bound together in a way, and it makes it more difficult for the water to be able to evaporate off. And so what we see is that lowers the vapor pressure, okay? And so here's our atmospheric pressure, and remember, atmospheric pressure is pushing down, and the vapor pressure is the pressure that's going to be above. And we see that the more particles that we have right above our solution, so if this is our solution here, and our solution break is right here, the more particles we have above, or these are water molecules that have evaporated, the higher the pressure. And so what happens is when those shells are there, it's much more difficult. There's a lot more energy required to evaporate, and so that lowers our vapor pressure, and there's not as many water molecules that are going to evaporate as easily. It's going to be harder for them to do that. They'll require a little more energy, which actually leads us into the next property, which is boiling point elevation. And so since that vapor pressure has been lowered, it's going to take more thermal energy in order to be able to boil or to get up to where the atmospheric pressure is equal to the the vapor pressure is equal to the atmospheric pressure. So if you remember, the reason why it's going to boil, so boiling occurs, okay, so we're going to boil when the atmospheric pressure is equal to the vapor pressure. And since our vapor pressure has actually lowered, we're going to have more energy in order to get into there. And if we have more thermal energy, so as we increase thermal energy, okay, we're going to have to do that by increasing the temperature. And so that's actually what will happen there. Our last one that we're going to take a look at today is going to be freezing point depression. And so this is actually going to lower the freezing point. So solute particles between water molecules prevent water molecules from really becoming quite as close. So if we have these water molecules, okay, so say I have an H2O molecule here, and an H2O molecule here, and an H2O molecule here, H2O molecule here, and we're trying to get these things to get closer together as we cool them down and they start to freeze. But if they don't have anything in between them, they're going to be able to come together a lot easier. But say we have magnesium chloride, and we'll just use magnesium in the middle here, they can't get as close together, and so it's going to require a lower temperature in order for them to be able to actually freeze. So with that in mind, we can actually go ahead and calculate these values for colligative properties. And so boiling point elevation, in order to do that, we have this equation. And so what this says is that the change in boiling temperature, which is the delta T of B, is equal to a constant value, K for boiling, times the number of particles times the molality. So let's get those on here. So K of B for water, which is what we're going to work with, is going to be 0.512 degrees Celsius per molal, okay? And so this is going to be a constant right here. This value here is a constant. Okay. And then we're going to see that we have P, and I use this, the book does not. This is the number of particles of solute that dissolve. So remember, if we're dealing with ionic solutions, then we're going to need to have more particles because they're going to dissociate. If we have something like sucrose or glucose, they don't dissociate, and so it would just be one particle. And then molality, and so that's going to be our moles of solute per kilograms of solvent. And finally, that doesn't get us our new boiling point temperature, so we have to actually add that to 100 degrees Celsius in order to find out what the new boiling point would be. Okay, so this is how we're going to determine the new boiling point, or boiling temperature. So that's what we do in order to find that with boiling point. With freezing point, it's actually quite similar as well. And so for freezing point depression, we have a similar equation. However, with that, we have a different value for our constant. So this is also going to be a constant, but this one is going to be for when we have freezing occurring. The P still represents the number of particles of solutes that are dissolved, and then the molality, of course, is still going to be the same. And so we actually have to subtract this change in temperature for freezing from 0 degrees Celsius in order to get it to be what the new freezing point temperature would be. So this is going to be the new freezing temperature. So those are our equations. So let's actually give this a try and see how it works for us. So on the next slide, here we go. What are the boiling point and freezing point temperatures for a 3.0 molal solution of calcium chloride? So the first thing that I want to do is I want to take a look at what my particles are. So the number of particles, remember this is an ionic compound, so we have an ionic compound. And that means that when calcium chloride is put in with water, H2O, we end up with a calcium ion plus 2 chloride ions. So this is what happens in aqueous solution, which means P is going to be a total of 3 particles. Okay, so with that in mind, we can go ahead and do our other calculations. So if I want to do the change in temperature due to boiling, okay, for boiling, we are going to put in our 0.1, oops, excuse me, let me erase that, 512. Okay. So 0.512 degrees Celsius per molal times our 3 that comes from over here. So this is going to be our 3 particles, and then multiplied by our 3 molal, 3.0 molal. Okay. And when I do that, I actually get a change in temperature of 4.6 degrees Celsius. Now remember, to find out our new boiling point, we are going to take and we're going to do 100 degrees Celsius plus our 4.6 degrees Celsius, and that gives us a new boiling point temperature of 104.6 degrees Celsius. So that's what our new, this is the change, this is the new, okay? So that is our new temperature there. And again, remember that this 3 came from the 3 particles that we determined that we have up here, okay? So that's where we're getting those values. All right, let's do this for the change in temperature due to freezing. So our constant value there is 1.86 degrees Celsius per molal. Okay, so that's our constant value. We still are dealing with calcium chloride, so we're still going to have 3 particles, and we also still have 3.0 molal. And so again, this 3 is coming from over here, okay? When we calculate that one out, we get 16.7 degrees Celsius is the change, okay? So that's the change in temperature. And then, so the new freezing point is going to be 0.0 degrees Celsius minus 16.7 degrees Celsius. This is how much it's gone down or depressed. And that's going to be a negative 16.7 degrees Celsius is going to be the new freezing point for that. And so we can take a look at all sorts of different solutions and how they would impact that. Just one note of caution, remember that covalent or molecular covalent do not dissociate. So they will just have one particle. So they are going to have one particle, always. I hope that was helpful. We'll take a look at some practice when we get back to class.